You have already learned about the physics of linear motion. Now we will consider rotational motion. The simplest example of rotational motion is called uniform circular motion. An object in uniform circular motion moves in a perfect circle with a constant velocity. When the object moves through an angle delta theta, it travels a distance given by the arc length delta s. You probably recall that arc length is equal to the radius of the circle times the angle. So, here delta s is equal to r times delta theta. If the time it takes to move through the angle delta theta is given by delta t, then the velocity of the object, v, which we assume to be this case, velocity equals delta s over delta t. Putting in r times delta theta for the arc length delta s gives velocity equals r times delta theta over delta t. If we define the angular velocity, omega, to be the change in angle with time, we find that the translational velocity v is equal to the radius of the circle r times the angular velocity, omega. The velocity vector is tangent to the circle at the object's position and is perpendicular to the radial line from the center. Notice that, as the object moves around the circle, the direction of the linear velocity constantly changes. Let's consider what happens when an object makes a complete circle. The time it takes to do this is called the period, and is usually denoted by capital T. The period is equal to the total distance traveled divided by the velocity. The distance traveled in one complete circle is equal to the circumference of the circle, which is equal to 2 pi r. Using the relationship we found for uniform circular motion, that the translational velocity is equal to the radius times the angular velocity, we find that the period is equal to 2 pi divided by omega. The frequency f is defined as 1 over the period. Since we just found that the period is equal to 2 pi over omega, we now have a relationship between the frequency and angular velocity. The angular velocity is also referred to as the angular frequency, which we now see is equal to 2 pi times the frequency f. You probably recall that the change in velocity with time is equal to the acceleration. Since velocity is a vector, an object is accelerated when either the magnitude or the direction of its velocity changes. This is a new concept, since until now we have considered only acceleration that results from changes in the magnitude of the velocity. As previously mentioned, the velocity of an object in uniform circular motion is constantly changing direction. Thus, this motion involves acceleration. This is called centripetal acceleration and is denoted by A sub c. Let's consider what happens when our object moves a small distance along the circle. The change in the velocity vector delta v is represented by vector v2 minus vector v1. We can graphically subtract the vector v1 from vector v2 to get vector delta v. Notice that delta v points toward the center of the circle. In uniform circular motion, the delta v vector always points towards the center of the circle it is describing, regardless of the object's position on the circle. We know the direction of delta v, which indicates the direction of the centripetal acceleration. Now let's find an expression for delta v over delta t to get the magnitude of the centripetal acceleration. If you look closely at the triangle formed by delta v equal to v2 minus v1, theta is the apex angle of the triangle. Since the magnitude of the velocity does not change, the magnitudes of v2 and v1 also remain the same. Thus, v equals v1 equals v2. since the triangle has two sides that are the same. It is an isosceles triangle. Now notice that the distance traveled by the object along the arc length is equal to the velocity times delta t. We can see that the small triangle formed by the radius and arc length is also an isosceles triangle with the angle of displacement equal to theta. Since the two triangles are similar triangles, the ratios of two sides of each triangle are equal to each other. Lastly, we replace the arc length by v delta t. From this expression, we solve for delta v over delta t, which is the centripetal acceleration. We find that the centripetal acceleration is equal to velocity squared divided by the radius. We found earlier that the direction of the centripetal acceleration always points towards the center of the circle. Thus, we have fully defined the direction and magnitude of the centripetal acceleration vector. The centripetal acceleration can also be written in terms of the angular velocity by using the relationship for uniform circular motion that velocity equals angular velocity times radius. Let's calculate the centripetal acceleration of the Moon orbiting the Earth. We'll assume the Moon's orbit is circular. We know it takes 27.3 days to orbit the Earth, and we also know that the distance from the Earth to the Moon is 385,000 kilometers. What is the direction of the Moon's centripetal acceleration about the Earth? Correct. Centripetal acceleration involves velocity and radius, but our given information is radius and period. Which of the given equations can we use to find the velocity of the Moon? Correct. What is the distance traveled by the Moon in one orbit? Correct. What is the Moon's velocity? Correct. What is the magnitude of the Moon's centripetal acceleration? Correct. The centripetal acceleration of the Moon as it moves around the Earth is quite weak, about 3,500 times weaker than the Earth's gravity. We will now go through an example of centripetal acceleration and the forces that occur in a loop-the-loop track. If the ball enters a loop fast enough, it will travel in a complete circle, and thus will have a centripetal acceleration directed towards the center of the loop. Let's analyze what happens at the top and bottom of the loop. If you have ever ridden in a loop-the-loop roller coaster, you know that at the top of the loop you feel lighter, and at the bottom of the loop you feel pushed down into your chair. At the top of the loop, the ball experiences two forces, gravity, which points down, and the normal force between the ball and the track, which also points down. The ball also experiences centripetal acceleration towards the center of the loop. Using Newton's second law, we can take the sum of the forces and set it equal to the mass of the ball times its acceleration. If we take up as the positive direction, the normal force and gravity both point down and are negative, and the centripetal acceleration, which also points down, is also negative. Now we solve for the normal force at the top of the loop. Since the normal force is equal to how hard the ball pushes against the track, it is equal to the ball's weight at the top. Here we will call this W top. Notice that at a particular critical velocity equal to the square root of gravity times the radius, the ball's weight at the top is 0. Thus, at this critical velocity, the ball is weightless at the top, and if the ball were to move slower than the critical velocity, it would not stay on the track. What happens at the bottom of the track? Here the force of gravity points down, the normal force points up, and the centripetal acceleration points up. Let's use Newton's second law to analyze this case. we must take care to keep track of the signs of the forces and the acceleration. Let's solve for the normal force. Notice that this time, the gravity and centripetal terms are additive. Thus, the ball's weight at the bottom, W bottom, is always greater than the rest weight of the ball, which is mass times gravity, with the difference being the centripetal term. As a result, the faster you go, the heavier you will feel at the bottom of the circle.